Yeah, tell me.
Um, the homework 4 we can submit on Sunday as well, right?
Yeah, yeah.
Okay, just to confirm.
Mm. All right. I guess we'll begin. So, good morning, everybody. Thanks for coming. Um, okay. All right. So, in the past two classes, I have introduced the harmonic oscillator, the problem of the harmonic oscillator to you, right? So that started out with a description of the Hamiltonian, and then an overview of how we go from the classical Hamiltonian to the quantum one, using the usual method of operator substitution. Then some reviews of some technicalities involving the position representation, etc. And then finally we end up with the Schrodinger equation for the harmonic oscillator. And it's just the usual Schrodinger equation. There is a kinetic term, there is energy term, and on the main thing aspect is that there is a potential term which has this form x square. Then the just a preview of the results of what we expect. We will see some quantization of energy levels. The potential of the harmonic oscillator is a parabola, right? Then the different ways to solve this differential equations. One way is to do it using series expansions. The other way is an operator-based method due to Dirac. So this operator-based method proceeds by first seeing that the Hamiltonian has the form of some two expressions, a square plus b square, and then the recognition that this term can be factored in a certain way. And then because these are operators and not numbers, we have to be careful about the order in which the numbers are multiplied with each other. And so we have this expression in which there is a commutator also. Okay. Then what we will expect to see later on is that these two factors can be written as operators, and it is clear that these operators are Hermitian conjugates of each other. So there's only one operator, and it's Hermitian conjugate. These are called ladder operators. Then I talked about how Hamilton's equations work in classical mechanics, and how this shows us that we do indeed get the solution for a harmonic oscillator from this Hamiltonian. And then in yesterday's class, we talked about the phase space picture of harmonic oscillator, showed you a picture of the trajectories for the classical solution, which are basically these elliptical trajectories in the phase space, and then explain what happens in the quantum picture. The trajectories become quantized. You have energy gaps. There are certain regions in the phase space where you cannot have any solutions. And then went over in a little bit more detail over this dimensionalist, over how to write down these operators, and explained in a little bit more detail how why we take these particular combinations, and that is so that these operators are dimensionless objects. And then I explained the procedure, the thinking behind it, and so I hope this was all clear. And then finally, at the end of the day, what we are left with is this Hamiltonian. And this is the Hamiltonian whose solutions we have to find. And in order to find the solutions, we will need to determine these commutators, which I had asked you to calculate. So hopefully you found the time to work through that. In any case, we'll work them out again today. So let's see what they are. So this is the Hamiltonian, and let me write down the expressions for these operators once again.
Hello, sir.
Yeah.
So, actually, I have a question regarding this.
So ask. Hello? Who has the question? Ask the question. Sudeep, did you have a question?
Yes, sir. Yes, sir.
So ask the question, no?
So the last equation we written, the H operator is equal to H omega naught A dagger into A plus half. Can we write this as H operator is equal to H omega naught A into A dagger minus half?
Sure, absolutely. So yeah, I'm coming to that. That is because of the way we write down the commutation relations between A and A dagger, right?
Yes.
So that's the next thing to talk about. So yeah. So this is the thing. And so the question is that so A and A dagger, they don't commute with each other, right? So let us ask, what is the commutator of A and A dagger? Okay. So the commutator of A and A dagger. So A dagger is this guy, A is this guy, and A dagger is Hermitian conjugate. Okay. Okay. So what will be the commutator of this? Right. So if you have some A plus B and C plus D, right? How do you find the commutator? The commutator is just, what is it? It's the product of this times this and minus the other one, right? So you will just get this, the commutator of AB plus BC, right? The commutator is also a linear operator. It is linear in the term. You will just get a sum of the linear term, right? So if I look at this guy now, what will I get? Well, I'll get a commutator of P, then I'll get plus x, right? but these guys are just going to be 0, right? Commutator of the operator with itself is 0, right? And then we get 2 more terms. So I get I times commutator of xp, and then minus I times commutator of px, right? And these two are the same basically, right? Because here the order of the commutator is switched. So I can just write this as 2 times I xp. Okay. You don't have to include these hats in every expression. If once it's understood that these are operators. Okay. And then what is this commutator? So then let us remind ourselves what is these two expressions, what is x and p. So this is p and this is x, right? So what is the commutator of xp? Right? First you'll get this factor, this guy, and this guy. These are just multiplicative factors, so you will get the product of this times this, and so m omega will cancel out. You will be left with 1 over 2 h bar, commutator of r small x and p. Okay, and what is this? This is equal to I h bar. So you will be left with I h bar by 2 h bar, which is just 1/2 I. Okay, and so what is this a dagger a again? A dagger a dagger commutator is 2i times xp, and xp commutator is I by 2. So I guess I'm missing a minus sign somewhere probably here, and so this will become 2i multiplied by minus I by 2, so you get 1. So a dagger commutator is 1. Okay. Now second. Right. Now, this is the first thing. So, because this is 1, what does this tell us? It tells us that a dagger minus a dagger is 1, right? That's the commutator. So, as Sudeep was asking just now, so I can always write a dagger a as a dagger minus 1, right? So if I substitute this expression a dagger minus 1 in here, I'll get a dagger minus 1/2, right? So I can write the Hamiltonian as in that way also. Why do we choose to write it as why do we choose to write the Hamiltonian? So we can write it like this, plus 1/2. We can also write it as a dagger minus 1/2, right? So why do we choose to write it like this, right? Why not like this? So there is a reason for this, which is the following. We'll come to the reason in a minute. Okay. First, so why this form? And not this one. So we'll come to the reason in a second. Okay. So first, before that, let us calculate two other commutators. So first we will give this guy a name. This is called the number operator. Okay. And we will see why it's called the number operator. And then let us calculate what this commutator is, A dagger A. Okay. So this becomes A dagger A dagger. Now, one of the problems in one of your homeworks was to show that if you have a commutator of this form, it can be written as A times BC plus this, right? So this was it in the homework, right? Was it in the homework or in the quiz? I forget. I think it's in the homework. In any case, you can prove this. This is very, very simple. This takes one or two lines to you just work out all the terms on the right hand side. You'll get some cancellation and you will see that it's equal to the left hand side. Okay. So if you apply this expression over here, you get, so this guy goes on the left, right? So when you look at this kind of a commutator, the term on the left is A, the term on the right is B in the product, right? So the left term comes out and is put on the left in the first expression. And in the second expression, the term on the right comes out and is put on the right. It's simple enough. The same thing also applies if you have so whether you choose, it doesn't matter what the order of your product is, of your commutator. So here your term on the left is A dagger. So I get A dagger times A, this commutator. And then the second term I get, this term on the right comes out and goes on the right. I get A dagger, A dagger. Okay. Now, this expression A dagger is 0. And I know that what is the commutator of A and A dagger? The commutator of A and A dagger is 1. So this, what does this become? This becomes A dagger. All right. So I am left with this result is equal to A dagger.
-1, no?
Huh? Sorry?
A into A dagger is -1.
No, this A dagger commutator is 1.
Yes, sir.
Sorry, sir, my mistake.
Huh? No, it's okay. I mean, again, these are all matters of convention. Again, one should not panic too much about such mistakes. So I make such mistakes all the time. It's not an issue. One should be careful, of course, in doing calculations because signs can always make a difference. Then we will also need one more commutator, which is the commutator of N with A. And N with A, you can do the calculation, and I leave this as a homework problem for you. And I mentioned this the last time, right?
Sir.
हाँ
Sir, can you correct the expression of commutator A, comma B, comma C? Sir, I thought this is repeating here. Sir, here somewhere will be also. Just one line above. Commutator of A, B, C.
हाँ भैया कर देंगे correct. There's no need to shout into the microphone. I can hear you. I can hear you. Relax. Okay. सुनाई दे रही है आपकी आवाज. ये लीजिए. हो गया? Happy? संतुष्टि मिल गई? इतने करेक्शन तो आप अपने आप भी कर सकते हैं ना. ठीक है. Okay, so now we have these two commutators, and these are the ones that we will need to basically solve the problem. Okay, so after this we will now ask, so we have this number operator. N, and so we have, it is some Hermitian operator. So first of all, N is a Hermitian operator. Why is that? Well, you can see that if N is equal to A dagger A, so if I'll ask what is N dagger, that is equal to A dagger, right? Then using the rules of taking Hermitian conjugate of products. So if I have two operators A, B conjugate, then this is equal to B conjugate, A conjugate. Okay? So if you do this, you get A dagger A. So this means it's Hermitian, right? So we know from our previous results that Hermitian operators have real eigenvalues, and that their eigenstates form a complete basis for the Hilbert space, right? So we will choose the eigenstates of N as a basis of the Hilbert space, okay? And we will label these eigenstates by we will call these eigenstates, let's say ket N, where N is the eigenvalue, right? So we will say that N acting on ket of small n just gives us, right? This is just the statement of the eigenvalue, right? We don't know what the explicit form of this n vector is yet, but we don't need to know it, right? This is just an eigenvalue equation. We can always I mean this you can say for any operator, right? You have some operator, it has some eigenvalues, some eigenvector. We can label those eigenvectors by you can call it this, right? You can also call it anything else you want. You can, right? So this is all very abstract, but it's also completely legal, and it's very very effective. So okay. Now let us ask what happens when I take this one of these operators. Let's say when I take A or A dagger, and I act on the N state. Okay, this is what we want to find out. Okay, what happens when I take this? So now for this purpose we will use these commutator results. Okay, so let's see how that works. Let's look at the first commutator. Okay, let's take this guy. Okay. And now, so let me write this as A dagger equal to, and n times A dagger minus A dagger times n. Okay. I'll just start on the next page. Okay, so now we want to ask what happens if you take A dagger and apply that to n. So we can take both sides of this equation, right? And we can write it like this. Okay. Now we can substitute this expression in here and see what happens. Get n times A dagger minus A dagger n. Get it. Okay. And now see, this whole time we don't know what the explicit form of any of these objects is. We don't know what the explicit expression for the number operator is or the station annihilation operator. I mean, we do have the explicit expression, I'm sorry, in terms of P and X, but we, I mean, we don't know what these eigenstates actually look like, right? So what do we get on the right side? We get n times A dagger n minus A dagger number operator acting on n. Okay. Now the number operator acting on n, what is this? This is small n times ket n. Why? Because as we said, this is the eigenstate. We have made that assumption, right? Okay. So Pranav, if you have a question, please just unmute yourself and ask. Okay. If there is some audio disturbance from somebody's side, then I mute that person. But you can always unmute yourself if you have any questions. Aman, if you have any questions, you please ask. Okay. Just now when you asked, it was just, I think there was a lot of noise in your background, and maybe that's why you had to ask a little bit loudly, and I got a little bit disturbed because of that. So don't mind my reaction. So now what we see here is, so we take this guy over on one side, n times n, and on the other side, what do we get? All right, because there's a negative sign here, so and then we take n times A dagger n minus A dagger n. Oh yeah, sorry, not this. What two is, yeah. So I take n times A dagger n, and I can write it like this. Okay, let me just work it out and then see. So n times A dagger n minus A dagger n is equal to n. So now in this expression, on the left hand side, so what I have done is I've just rearranged these two terms. I've just taken this term, so I have taken this term, brought it over to the other side, so I get minus a dagger n, and then I've taken this guy and put it on the other side. So I get plus a dagger n. Oh, right. That's my mistake. That's why I'm right. So this whole term becomes minus n times a dagger n. Right. Now everything is working. Great. So now I can bring this term over to the left side. So if I bring this term over to the left side, what do I get? This is equal to n times a dagger. Okay. So everything's fine. We are good. Now on the left side, we can write it as n plus 1 times a dagger n is equal to n times a dagger. And this is the result that we wanted. Okay, this is the result that we need. So I hope that you've been able to follow this. Let me see. Let me quickly check on YouTube if there are any questions. Okay. No questions on YouTube.
So does this mean a dagger n is an eigenstate of n?
Shanti.
Okay.
Yeah, that's what it means. But I was just hoping to make that great revelation. So now if you look at this expression, then let us collect this expression. In this expression, we have a dagger n. And now, so a dagger n, let's call this some state phi. So what is this expression telling us? This expression is telling us that if I take the number operator and act on phi, I get small n plus 1 times phi. So that means that, as Shashwat also pointed out, phi, this means phi or a dagger time acting on n is an eigenstate of n with what eigenvalue? N plus 1. Otherwise, people will think it's a factorial. It's an eigenstate of n with eigenvalue n plus 1. So that means that phi, right, is what? Phi is what? Phi is the same as this state. N plus 1. Okay. All right. But now, so it's not, it doesn't have to be equal to this state. It can be proportional to the state. So we have not yet normalized these states. Okay. So because you can always take this and multiply it by some factor on both sides, and you will still get the same equation, right? So this is just a proportionality relationship at present. So let me just go over this again. We start with the commutation relation between a and a dagger. Then we write down the number operator. We calculate the commutator between the number operator and a dagger, that is a dagger. And similarly, the commutator between the number operator and a, that is minus a. Then we assume that there is a set of eigenstates of the number operator, which we label by the eigenvalue n. Then we ask what happens when we act on n, this get n with the A dagger. And then we use this commutator relationship. So A dagger can be written as the commutator of n with A dagger. Expand it out, act on n. On the right side, what do I get? I get n times A dagger, this expression, times the get n. Then the second term is minus A dagger n, A dagger times n acting on get n, number operator acting on get n. The number operator acting on get n gives me small n times get n, because by assumption this is an eigenstate of number operator, right? And so the whole expression, this second term on the right, becomes minus n times A dagger acting on n, right? Because small n is just a number, so I can bring it to the left of A dagger. So now I can take this guy and put it on the left and add it to this expression. So I get A dagger get n plus n A dagger get n is equal to this expression. And then we notice that A dagger n is an eigenstate of number operator with eigenvalue n plus 1. Okay. Similarly, using the exact same procedure, one can show that if you take A and act on n, right? So if you act on A with n and you say that, well, this is some other state, let's call it phi prime, then phi prime will be an eigenstate of n with eigenvalue n minus 1. Okay. So this is the reason that we call these A and A dagger as raising and lowering operators, right? So if I start with n and then I act on it with A dagger, I get n plus 1. And if I take n and act on it with A, I get n minus 1. And there are some proportionality constants. We'll work them out in just one second. Okay. So is this clear so far, I hope? Are there any questions about this? No? Okay. All right. So now the question is, what is this proportionality constant? So we have that A dagger n is equal to some number c times n plus 1. So then we have, what is c? Okay. So if you want to calculate c, well, what can we do? We basically want to find the norm of this state. Okay. So how do we find the norm of any state? We take phi. This is the expression for the norm of the state, right? Or the norm squared, right? So let's take this state. This is our phi state, and calculate the norm. Okay. So I have to take the bra vector of this expression, A dagger n. So the bra vector, if you remember, is the Hermitian conjugate of the ket vector. And in this case, our ket vector is A dagger n. And then using the rules of Hermitian conjugation, we know that this can be written as bra n times A. Okay. So what do I have finally? I have A dagger n. I want to take the norm of A dagger n. So this is phi. And then the bra vector is this expression. So if I take the inner product of these two, what do I get? I get n A dagger n. Okay, I've gone through these steps a little bit slowly. I mean, they're very, very simple and straightforward. I could just have jumped from this expression to this expression without going through the intermediate steps. But I've shown them so that in case there are any doubts, those doubts are cleared. Okay. All right. So this is the norm. Okay. And now, what is A dagger? A dagger, if you will remember, A dagger is equal to A dagger A, right? We have the commutation relationship between A dagger and A. So we can write A dagger as A dagger A plus 1, right? So this becomes n times A dagger A okay. All right. Now these eigenstates, these n, we can take them to be normalized, right? That means n times n is equal to 1. All right. So then this becomes equal to 1. And what is this A dagger A? This is equal to the operator n. Operator n acting on ket n gives me, so this becomes equal to n, number n plus 1. And then this becomes n times n plus 1, right? And then again, this is equal to 1. So this just becomes number n plus 1. Okay. And so what is this n plus 1? This is n A dagger, right? This is the norm of the state phi, or the norm squared of the state phi. So what is the norm? What is phi? Phi is what I get when I act on A dagger on n, get n with A dagger, I get phi. And the norm of that state phi is n plus 1, right? And remember that I said that we know that phi is proportional to ket n plus 1, right? So phi is equal to some constant c times ket n plus 1. And n plus 1 is a normalized state. So what should be the value of c? Anybody?
Root n plus 1.
So c will be equal to root n plus 1.
So won't norm C be equal to root n plus 1? Because C is a complex number here.
Root norm of C. What do you mean by? I mean,
Absolute
if
of
I,
C.
so you are saying that there can be some complex phase. Is that what you're saying?
Yes, sir.
Sure. Throw in a complex phase if you like. It's not going to change anything. Okay.
Okay.
Yeah. You can always throw in a complex phase. Yeah. But in this case, it won't affect anything. So we leave it out. Okay. So what we get is A dagger n is equal to root n plus 1 times get n plus 1. Okay, in exactly the same way, you can show that A times n is equal to root of n times n minus 1. Okay, this you can again show. So finally, we have shown that A and A dagger are ladder operators. They increase and they decrease the eigenvalue of this n by 1. Now, what is this ket n state? Now, remember the Hamiltonian can be written as H. Right? This is a Hamiltonian, right? So, what is the action of the Hamiltonian on these n operators, on these n states? What is this? This is just equal to h bar omega times number n half ket n. Right? And you remember that Hamiltonian is the total energy. This is the energy operator, right? Basically. So this tells me that what is n? N is an energy eigenstate, right? With what is the energy of this eigenstate? It is h bar omega times n plus 1 half. Okay. All right. So essentially, we have solved the harmonic oscillator problem. Okay. The only thing that remains is to determine what is the maximum and minimum values of this n. Is there a maximum value or a minimum value? Okay, so we know that n is a real number, right? We can show that it has to be a positive number. How? Well, let's take a look again at this A acting on n. And let me take the norm of this state. So the norm of this state will become n like this. And this is equal to this operator n hat. So this becomes n times n times n. This becomes equal to n. So this guy n, this number n, is equal to the norm squared of the vector A acting on n, right? And the norm squared of any vector is always greater than on 0. Right? This is the basic property of norm, right? The norm of any the norm of any state is always non-negative. So that means n is also non-negative. Okay. So n has to be greater than or equal to 0, which tells me that the eigenvalues of H, what are the eigenvalues? H bar omega n plus 1/2, right? These eigenvalues always have to be greater than or equal to H bar omega by 1/2, because n always is greater than or equal to 0, right? So if the lowest bound is that n is equal to 0, if n is equal to 0, then the lowest eigenvalue is H bar omega by 2, right? So for n is equal to 0, what do we find? We have that the energy is H bar omega by 2. Okay, and what is this? This is the ground state energy of the system. So the ground state energy right? So the ground state energy is not 0. And if you remember, this is the same thing that we found for the particle in a box. For a particle in a box also, the ground state energy was not 0. Right? So then this brings us to a question. E naught is not equal to 0, right? What does this imply about the area enclosed by the trajectory in phase space, right? So in phase space, you remember the system moves in these elliptical circles, right? So what will happen is that the lowest energy, this E naught, right? It is non-zero. So that means that basically what that means is that the trajectory cannot shrink below a certain size. So another way of saying that is that the area in phase space cannot be less than a certain minimum value. Okay. Now, if you look at phase space, what is phase space? It is x and p. Now, x and p, these are classical variables, you have to remember. Right? And for these classical variables, in terms of these classical variables, what is the meaning of an area? This is an area, right? So what is this length? This is delta x. This is delta p. Right? So what do we have is that this area A minimum, this is always greater than or equal to some value A naught. It can never be smaller than that amount A naught. So this tells us that delta x times delta p is always greater than or equal to A naught. Right? And what is this? This is a statement of the uncertainty principle. Right? So if you have a classical particle, the classical particle can move in any trajectory, right? If you have a classical particle moving in phase space, the classical particle can move, it can go to trajectories which are arbitrarily small, right? Or if you're moving in this part of the phase space, it can go to arbitrarily small areas, right? But if you have a quantum particle, then the quantum particle, the trajectories are limited. This is also related to the fact that there is a fuzziness. There is a fuzziness in this. In fact, you can't have these, you can't really have such sharp trajectories in for a quantum particle. For a quantum particle, you can imagine having a trajectory like this, but around this trajectory, there is always a region whose area is around A naught. So it's like a fuzzy ball moving around in the phase space. You cannot have a single point, a well-defined trajectory. Instead, you have a fuzzy trajectory. Right? So this is an example of the uncertainty principle at work. Okay. So I'll leave it here for now, and this basically covers the harmonic oscillator, at least the Dirac quantization of the harmonic oscillator. For the MSc students, we have to go back and we have to actually look at the other solution also in terms of Hermite polynomials, not for the BTech students. But there is one problem that you do need to prove, and I'll give it to you as homework problem, which is that you can prove this. And then right. Okay, so I'll leave it here for now. Any questions?
So my question is slightly deviating from whatever is being taught in class today. Like for a free particle that is suspended in space, how will the wave function be?
Well, when you say it's suspended in space, how is it suspended in space?
You just let it go. Like you give it some energy and then there is no potential that's acting on it.
Right. So its wave function can be whatever you want it to be, no? Right. Okay. I mean, the eigenstates will be plane waves.
Okay. So, but for the plane wave at minus infinity and infinity, it's not zero.
No. But you can take superpositions of those plane waves, no? Those are the eigenstates. That is not the state. The state can be a superposition of those plane waves, right?
Okay. Yeah. So that will give us like a packet of wave or something.
A wave packet, right? So it'll be a wave packet.
Okay. Thank you, sir.
Yeah, Vipul, the commutation relationship is just that, yeah. If you take, I mean, in this particular case, I have two operators, let's say A and B. If I take the commutator of A with B, I just get B. right? That's the property of this A dagger. And if I take A, then I get minus A. That's just a particular property of these operators, A dagger, and N. And it is this property that allows us to solve the full system of the Schrodinger equation for the harmonic oscillator. This is not going to always be the case, right? But you can see that whenever you have an operator A and its Hermitian adjoint, such that these two, the operator and its Hermitian adjoint, have this commutator. Again, that does not need to be the case, right? An operator and its Hermitian adjoint need not have this commutator 1. It can be something else. It can be 0. It can be some function. It need not be a constant. But if it is this 1 or some constant, then you can construct this guy from A and A dagger, which is a Hermitian operator by definition. And this Hermitian operator, when you take the commutator with A dagger, you get A dagger. With A, you get A. So it all boils down to the fact that this property is satisfied. So this is true for this particular operator, A. It will not be true in general for any arbitrary operator. You take some arbitrary operator O, and you say that what is the commutator of O in O dagger? Is it equal to 1? Right? And the answer will be no.